Спасибо. Доброе утро. Спасибо, что добрались. Несмотря на погодные условия, мы все-таки ожидаем, что сегодня в течение дня к нам приедут все оставшиеся зарегистрировавшиеся. Мы начинаем второй день нашей конференции. Специально для удобства поставили микрофон в центре, если будут вопросы, чтобы вы подходили и задавали. Сегодняшний день будет не менее интересный и насыщенный, чем вчера. И начинает нашу программу Кирилл Струминский с мини-курсом. Кирилл, вам слово.
Анна, спасибо за представление. Скажите, пожалуйста, наверное, мне нужно на английском языке выступать, да? Is there anybody who does not speak Russian?
У нас будет запись, поэтому вполне правильно будет сделать курс на английском, для того, чтобы его посмотрели
maybe
все
later
желающие.
someone will arrive who didn't hear the question, so the question is useless. Okay, thank you for the introduction again. In these tutorials, I wanted to cover topics related to machine learning with 3D data. These are the topics I've been working with colleagues on for several years, and the tutorial will be an overview of works which I consider to be key works in these areas. And the specific areas I'm going to cover are 3D reconstruction and its complement, 3D generation. So let's move on to agenda for today's tutorial. First of all, we'll discuss computer graphic basics in a bit. In order to be comfortable with working with 3D data, I'll show some examples and some motivational tasks. And then we'll move on to discussing neural fields. So mainly the first part of the tutorial will be devoted to neural fields, which is a key technology behind the boom in 3D reconstruction of the past several years. And the task they are intended to solve is called novel view synthesis. We'll discuss the task and the recent advances in solving this task. And during the second part of the tutorial, we'll continue with the task of 3D generation, which is very similar to text-to-image generation you may be familiar with. But instead of generating 2D images, we'll be generating 3D images. However, we will still be using diffusion models, which have only seen planar data, that is, images. And we'll discuss how to leverage a pre-trained 2D model to generate 3D data. I consider this topic to be quite exciting. Okay, so let's move on to basics of computer graphics. We'll start with some motivational questions and examples. So the task is, the question is, first of all, how do we represent data and what kind of data are we supposed to work with? So what kind of data can we encounter? Well, the world we live in is essentially three-dimensional. We perceive it as three-dimensional. And three-dimensional data comes from many tasks. However, 3D data is much more sparse than, for example, images. There are millions of images available on the internet, but 3D data is harder to acquire. However, it still comes from very relevant and important tasks. So in this slide, I grouped data in two example categories. So first of all, it's navigation in robotics. As far as I understand, the original intention behind developing computer vision was not classifying cats and dogs and all this stuff, but enabling machines to see, to design robots that can operate in real world. Well, with development in deep learning, we essentially moved to classification and tasks that are far from robotics. But now, as we return to tasks that are related to 3D data, we sort of return to navigation tasks and mapping tasks in robotics. In this slide, I have several examples. So the pictures I show represent data that comes, for example, from driverless cars. From driverless cars, we can obtain two kinds of data. For example, data from cameras, which is cheap, but it's hard to estimate depth and reconstruct a scene. So usually you don't use only one camera. For example, Tesla uses several cameras, and with several cameras you get richer data. And even and if you have more money to spend on sensors, you can get a LiDAR, which returns point cloud that represents a 3D scene. So in these examples, data comes in forms of pictures or point clouds. The other group of applications, I call it visualization. And there are several tasks I'm pretty excited about. For example, the machinery we're going to discuss today comes essentially from applications to MRI. MRI is a machine which is an abbreviation for magnetic resonance imaging, and it tries to recover volumetric data from indirect measurements. And so the neural fields we're going to discuss, they essentially use tech which was developed to visualize volumetric data. Another example is electron microscopy. So this is an application which was developed several years before NERF was presented. NERF is the topic we're going to discuss later. And in this task, instead of encountering objects on our regular scale, we work with objects that are in much smaller scale, namely molecules. And in this application, we freeze the substance we want to analyze and obtain multiple pictures of molecules from different angles. And with these pictures obtained with a microscope, we want to reconstruct 3D structure of the molecule. Why would we want that? Well, it turns out that knowing just chemical formula for a molecule is not enough to predict its properties. Usually it's important to know the structure of the molecule, and it's hard to predict the three-dimensional structure of a molecule just purely from a chemical formula. But with these tech, we can reconstruct almost automatically 3D structure of, for example, DNA molecules or some proteins. And the last application, which is, I guess, much closer to day-to-day life, is video conferencing. Probably some of you have seen a demo of Oculus video conferencing where you put a headset on and it renders a 3D model of you and shows it to your to a person you're talking to. This tech has been developed for several years now, and there's a rival project at Google which aims to deceive you into believing that you're sitting in front of a person you're talking to, when the person is actually sitting like thousands of miles away, for example. And in this picture, there are two people. Well, this person is a real person sitting in front of the photographer, and this person is not a real person. It's a person projected onto a flat screen. And this screen gets information from far away and renders a 3D model, and it takes into account the movement of eyes of the person looking at the screen, and models projection to deceive you that you're looking at a 3D model, not at a planar projection of a person sitting in front of camera. I guess the slides will be available, and I really encourage you into looking into some of the references. There is an exciting video representing this technology. Well, a picture cannot show how impressive this is. So I encourage you to look at the video later. Okay, so now that we've covered some of the application, let's discuss how could we represent 3D data. And there's a classic classification for representing 3D data. So usually data representations are divided into explicit representations and implicit representations. So explicit representations, I guess, are most common these days. And these include, for example, point clouds that can arise from depth sensors, for example, in driverless cars or in your phone. Another common representation of data is polygonal mesh. Well, I can see the pointer, so I will not show with the pointer. Okay, polygonal mesh. So essentially, you approximate your body with a surface, which consists of, for example, triangles. And another representation is parametric, for example, like splines, where you have several parameters that you transform into smooth surface. So parametric representation has an advantage over polygonal mesh that this representation leads to smooth surfaces that can have nice aerodynamic properties. But all of those representations are nice from the viewpoint of computer graphics, but they are not as handy from viewpoint of machine learning. For example, when you work with polygonal meshes or parametric representations, you cannot modify the topology of the surface you represent. So if you start with a sphere and you want to run a gradient descent and turn sphere into a mug with a handle, you will not be able to do this just by moving around vertices of a polygonal surface, because the connection structure of the surface is fixed, and it's an object of discrete structure. You cannot modify it with gradient descent. Another issue is that, well, when you work with deep learning, you usually aim to design systems that are differentiable with respect to any parameter you have. Well, for example, you have an output of your network, like an image, and you want to be you want to differentiate an image with respect to each parameter of the network. If you draw an analogy with computer graphics, in computer graphics you draw an image, and you want to compute the gradients of an image with respect to the parameters that an image has, for example, locations of vertices. And it turns out that the classic algorithms that are used to draw these images, they are not differentiable by default, and usually it takes a huge effort to transform these algorithms into algorithms which are compatible with machine learning solutions. Okay, so let's move on to another type of representations, implicit. While explicit representations mapped, they dictated where are the points of the surface, so you were able to compute the exact locations of points on the surface with these representations, for example, by taking a point on a point cloud or taking a point on the surface of a triangle in polygonal mesh. Implicit representations, they do not allow you to find points on the surface as easily. And a classic implicit representation is isosurface representations, where you have a function, and you say that your surface is a level surface of this function. An illustration of such a representation is the picture in the bottom, where you have a function which is red inside the shape of this duck, and it is green outside of the shape. So green values are positive, red values are negative, and white surface between green and red areas is the surface that you're trying to model. The representations we're going to talk about are related to are essentially implicit representations, but they are not isosurfaces. Well, because surfaces are an abstraction which has its own drawbacks. So today we're going to move on from an assumption that the object which we're trying to represent can be represented as a surface, and we will use so-called volumetric representations. So as I've already said, saying that an object you're trying to represent is a surface is a sort of mathematical abstraction. It works in most of the times. For example, like most of the rigid bodies, all of the rigid bodies you can represent as a surface. But sometimes these bodies are so complex in their shape that representing them as a surface is impossible. If you want to, for example, draw a tree, you'll have to model each leaf, each branch with, for example, a polygonal mesh, and this representation will take a lot of memory, and it's not feasible to represent trees as polygonal meshes. So this picture illustrates a photogrammetric reconstruction of some area. In this picture, the algorithm succeeded in representing houses on the map. These houses are, they have regular shape, they're square, maybe a little rounded, but next to a house there's a tree. And while trying to represent the tree with a surface, this algorithm gets completely confused and outputs crazy polygonal soup that is nowhere near to the exact surface of a tree we're trying to represent. On the other hand, the algorithms we're going to discuss today, they are perfect for representing such detailed structures such as trees, human hair, and even some transparent objects that are also hard to represent as surfaces. Okay. So what is a volumetric representation? This will be an implicit representation, but instead of using an isosurface of a function, we will use another kind of function, which we'll treat as some sort of density. It will be a function that takes a spatial point as an argument and returns a scalar value, which says, is there something in this point or not? So this scalar value will vary from 0 to plus infinity, and it will be equal to 0 if there's nothing in this point, if this point is empty, and it will be positive with some values if the point is not empty. I guess this idea is pretty intuitive, and I will foreshadow the terminology I will use for these kind of functions. I will say that this function is a scalar field. A field is a term which is common in physics, which essentially is another name for a function that takes a point, for example, in space, and returns a vector or a number. So this is a scalar field which takes a 3D point and returns a number. Okay, and the density from the physical viewpoint will represent the amount of light that passes through this point in space. For example, if we're talking about air, air allows light to pass without any problems. But rigid surfaces, such as this desk, it does not allow light to pass, and it will have high density. Okay, a few more words about vector fields. I wanted to underline that this object, this idea of a vector field, is a pretty handy notion for representing various kinds of data. So, as I've already mentioned, most often this term is used in physics, but data we're working with can be also interpreted as a field. So I have a few examples here. So the first example is on the top left. It's some sort of vector field that can come from physics and model some sort of force in space. Okay, and the other three examples are more relevant to today's topic. So the top right example is an example of an X-ray image, which is essentially a map that says how much light passes, how much light passes through this part of space. So in this image, there is a glass of wine and a bottle of wine, which allows some portion of light to pass. For example, there's a metallic Kindle, which does not allow the X-rays to pass, and it's not as transparent as the other parts. Another example is a sign distance field, which is another way of talking about isosurfaces, but instead of representing a surface as a surface level, we'll put additional assumptions on the representations. We'll say that at each point in the space, the value that the field returns is a distance to the closest point in space. These additional assumptions allow us to design more efficient rendering algorithms, and it's a quite useful representation in computer graphics. And the last example, which will also arise several times during the talk, is an image. Usually we think about images as some sort of tensors, which are three-dimensional, with one dimension being 3 or 4, and other dimension being like thousands. Another way of thinking about images is thinking about it as a vector field, where your input space is planar rectangular, is a box, and you query a point in this box, and you return the color of this point in the image. So this is a vector field that is defined over a plane, and it returns a 3D vector, which represents 3 colors in the image. Okay, now that we've discussed vector fields and their different phases, let's move on to the term neural fields, which is central to this topic. So a field is an object that takes a point and returns a vector or a scalar value. And several years ago, there were several seminal papers published that studied the idea that you can represent fields with neural networks. So, for example, if you want to represent an image, usually you store values of colors for each location. But instead of doing this, some of researchers proposed to do the following. Let's train a neural network that will have low-dimensional input, namely a point in space, and it will also have a low-dimensional output. For example, the color of an image or like some scalar value. And let's train a network to approximate the data that we have. And it turns out that not only neural networks are useful for machine learning applications, they are also useful for modeling fields. And in this slide, I show several examples from one of the seminal works called Siren. in which the authors explored representing images, audio signals, and even video data with those tiny neural networks. So let's look at the examples. So they succeeded in representing photos, and they show that careful selection of architecture can really improve the quality of rendering. And they succeeded in representing audio signals, and it's very impressive. They tried to represent raw audio signals with tens of thousands of input values, time steps, and they predicted the location of speaker membrane at each time space. And surprisingly, it is possible to model to compress audio signal into a single neural network. And another application, which is more visual, is representing video data with neural networks. So here, they took a video fragment, which can be seen as a four-dimensional field, three-dimensional field, sorry. Apart from having two spatial coordinates, they also added a time coordinate to change frames. And for each of those three coordinates, two spatial and one temporal coordinates, they predicted a color of a pixel. And it turns out that if you take a simple multilayer perceptron with several fully connected layers and a perceptron which is not very big, which with, for example, 8 layers and hidden dimensional size of 500, you'll be able to train this perceptron to reconstruct your data. So if you take a naive architecture with ReLU activations, you will also be able to reconstruct the data, but it will be blurry. The thing that the authors proposed is to add additional activations that allow to reconstruct sharper transitions on the images easily. What am I talking about? Let's look at the video. So in this video, the right part is a video reconstructed with a ReLU network, and the left part of the video is a video which is reconstructed by a similar architecture, a multi-layer perceptron, but this time it has a different kind of activations. Let's look at the video. So as I've already said, the video on the left is much sharper, and the video on the right is blurry. And as far as I understand, this is not a shortcoming of the architecture itself. It is possible to model video even with an architecture with ReLU activations. But it seems that training with special positional embeddings is easier, and it leads you to better reconstruction quality in less time. Okay, so these are more common types of datasets which are available in vast amounts on the internet: images, audio signals, videos. Let's now move on to 3D data. Okay, so first of all, I'll tell you about the problem setup, and there's a thing to be careful about in this setup. I will talk about it. So the task we're going to discuss from now on is called novel view synthesis. And the task is formulated in the following way. So we have a set of images, a set of images of a 3D scene taken from different viewpoints. And for simplicity, you assume that you know these viewpoints in advance. It's not hard to reconstruct these viewpoints, and we'll assume that we know these viewpoints. And we also have some sort of test data, and test data in this case is a novel viewpoint from which we have no images of the scene. And the goal of novel view synthesis is to render a picture of the scene from this novel viewpoint as if we knew what was the model, how it looked from this novel viewpoint. So you can think of this task as 3D reconstruction. So in order to draw a scene from a new viewpoint, probably you have to know how the scene looks like. But be careful, you're just asking for an image from a novel viewpoint. It turns out that it is not necessary to have a perfect 3D model of an object you're trying to render in order to render a sufficiently good image. So the task does not really care about if we know what was the shape of the scene or we don't. The task only cares about our ability to draw the scene from a novel viewpoint. Okay. So now after defining the task, let's move on to the way we can represent our scene with a neural field. So the technology used to represent 3D models was named neural radiance fields, and we'll understand why was the name chosen like this in a moment. So again, as I've told you before, we're going to represent the shape of our scene with a volumetric representation. We're going to define a function, which I'll refer to as sigma or as density, that will take a spatial point and tell me how much of the light passes through this point. Is this point transparent or not? And in order to draw beautiful shapes, in order to draw convincing images from new viewpoints, I'll also have to find out what is the color of the point that I'm looking at. So in addition to defining a density function, I will also define a function which I will call radiance function, which will also be a low-dimensional field that takes three-dimensional point and a point on a sphere and outputs a three-dimensional vector, a vector which tells me what are the colors of the point. So there is a very important detail here. The function takes not only the input position in space, but it also takes a point on a sphere. What is the point? I'm not going to ask questions in the audience, but you may try to think about why would we need such a point? Just for a couple of moments. Okay. Now I'm going to tell you the answer. Well, it turns out that light is a pretty complicated substance, and many of the objects you encounter in real life, they change color as you change the point of view that you're looking from at this object. And in this picture, I pasted an image of a shiny sphere with almost perfect mirror surface. And when I will start the video, the image on the sphere will change as we move around the sphere. So each point of the sphere changes color as we change the viewpoint. So in order to model this effect, in order to model the behavior of light in the real world, we'll also add a dependence on the viewpoint that we're looking from. Great. Again, a few words about the architecture we're working with. We'll work with, for the first part of the talk, with multi-layer perceptrons. These are extremely simple architectures. The architecture I will going to use is a fully connected network with 8 layers, with sizes of layers 256 by 256. And the only nuance that this architecture has, the only important nuance, is that instead of taking point as it is, It will use positional embedding of the point. And the positional embedding I'm talking about is just the copy of positional embedding solution that is used in transformers that transforms a 3D point into a vector of sinuses and cosinuses in order to represent a position and be able to use it inside of the neural network. Okay, now we have a representation of a scene, and this representation is sufficient to model a vast variety of real-world phenomena, rigid bodies, fluids, complex shapes such as trees, hair, and it consists of two components: density, volumetric field, and radiance field. Now, as we know those two components, let's discuss how would we generate an image from a novel viewpoint. So I will discuss a camera model in a few words. The camera model is taken. So the camera model that is usually considered in computer graphics and computer vision is usually the simplest camera model possible. It's a camera called pinhole camera, which can be thought of as a shoebox with a small hole on the side of a box. And the light that is casted from the scene is passing through this hole, and it projects on the back surface of a box. So this is the model, and this is exactly how the light works in real life. For example, if you cover windows in a room to cancel all the light and make a small hole, you'll see a projection of the image outside of your room on the wall. And this model says that, well, each pixel of an image is generated by a ray that comes to this pixel from some point on the surface. So in order to compute a color of a pixel on an image, we'll have to do the following thing. We'll have to select a pixel we're going to generate, then construct a ray that passes from this pixel to the pinhole and then goes out there beyond until it encounters some surface on a scene. For example, a leaf on a tree. And then as the ray intersects a leaf on a tree, we compute the color of a leaf. We know that it's green. And then we write down that, well, this ray encountered green color. Therefore, the pixel color in this position is green. And in order to generate an image, we'll have to cast rays and do this procedure for several millions pixels that comprise the whole image. I wrote some pseudocode here to illustrate how this is written. Well, because running NLPs probably is not as threatening or sounding complex as modeling real-world cameras. And I wanted to convince you that the procedure behind this camera is also pretty simple. So we take a point on a plane, a pixel coordinate. We take a focal length, the parameter which says how far is this side of a shoebox from this side of a shoebox. And then we take a parameter t, a distance the light travels till some point on array. So in order to generate a point on array, we take array origin. It will be the position of this pinhole. And we'll compute ray direction. The ray direction is essentially a difference between ray origin, the pinhole position, and the position of a pixel. So the position of a pixel is xy, positions on a plane, and also f, the distance between the origin and the other plane. So in order to compute ray direction, we just compute this vector, and then the ray point is a sum of ray origin plus direction times distance we travel. If we wanted to cover ray with a multitude of points with some grid, we'll just have to take multiple points t and repeat this procedure for different points t. Okay, and what does the focal distance contribute? So the focal distance essentially contributes the amount, the view field that you have. So if the focal distance is large, the shoebox is wide, only a small ray, a small cone of ray will be able to pass to the other side of the box. And if the shoebox is thin, the field of view will be very wide. And I also added a GIF to illustrate. This is a video of a colleague of mine taken with an iPhone, where I changed focal distance to illustrate how it works. So here I gradually switch from portrait mode to wide angle mode. And it really changes the face and distorts geometry. So this parameter is quite important. Okay. So now that we know how camera works, how do we compute the color using our representation? So on the previous image, I told you to find an intersection of a ray with a surface and compute the color of a surface. But with volumetric representations, we no longer assume that there's some sort of surface. And instead, we accumulate a color from all points on the ray. Some points are transparent, and they contribute no color to the output pixel color. And some points are opaque, not transparent, and we have to get the color of these points and add them to compute the output color of a pixel. Here I put several illustrations. This is an MRI image, and this is an image of a cloud. As I've already mentioned before, those solutions were primarily developed in order to facilitate MRI imaging and to allow researchers to view different MRI reconstructions of human body. And also, those representations were quite popular in computer graphics for modeling volumetric effects such as clouds or fog. And by the way, I didn't mention it, but it's impossible to represent a cloud with a polygonal mesh because there is no surface on a cloud. The cloud, it does not have a surface. But those solutions, like volumetric fields, they are great for representing clouds. Okay, how do we compute color? There is a physical model behind this, which we could have discussed, but I think this physical model is quite unnatural and counterintuitive, so I will only tell you about the exact algorithm that is being used in rendering these days in neural radiance fields and those applications. And the algorithm goes like this. So we want to find out what is the contribution of our scene to the output color of a pixel we're looking at. And in order to do this, we cast a ray and split the ray into multiple segments, which are better to be smaller. And at each segment, we compute the following quantity. So we take our density field, which was a scalar value from 0 to plus infinity with some physical intuition behind it. And then we map it into a scalar value, which I will denote as alpha. So what is alpha? Alpha is a value between 1 and 0, you can see. So there's a negative value in exponent, and exponent varies from 0 to 1. And this alpha tells you the opaqueness of our pixel, the opaqueness of our point in space. Let's look at how it works. So imagine that sigma is 0. You'll have exponent of -0, it will be 1, and alpha will be 0. So alpha will be transparent. And if sigma is huge, like hundreds, sigma times the size of the interval will be also non-zero. Exponent will be closer to 0, and the output alpha will be closer to 1. This point in space will be opaque, not transparent. And after computing those alpha coefficients for each point on array, want to compute the color on array. And this color is computed with this formula, which computes color at segments I, and then multiplies these colors by a weight coefficient. What is the idea behind weight coefficient? So this weight coefficient has to take into account the following effect. If we see a non-transparent surface near us, we will not be able to see the stuff behind this surface. And this is modeled with this discount term. So this discount term, I'm pointing at the product. The product will be non-zero only if all the alpha values before the position I are close to 0. They are transparent. So if all positions before I are transparent, then position I will contribute with weight alpha I, color C of Ti. And if we go after a non-transparent point, we will encounter a 0 term in the product, and the overall weight will be 0. So this algorithm models this effect. And another reference I really like to add here is that whenever you work with layers in Photoshop or in Keynote presentations, and you combine images at multiple layers, this algorithm that I wrote below is the algorithm they use to combine images on multiple layers. This algorithm is called alpha compositing, and alpha is a letter which I deliberately chose to represent the opacity channel, which is usually the fourth channel on our image. Okay, so this algorithm is pretty classic. It is used in MRIs, in Photoshop. And nice feature of this algorithm is that it consists of operations that are extremely nice. What are the operations? So we compute sigma with some neural network, and then we pass sigma into exponent, which is differentiable. We combine these exponents with products and sums. Those operations are also very nice. And the algorithm we end up with is differentiable with respect to all the parameters we have in the scene. It's differentiable with 2 sigma. It's differentiable with output radiance. And we can differentiate it and compute gradients with respect to density and with respect to color. And this algorithm is extremely simple. It takes a few lines of code to program it, and it does not require any effort to make rendering with this algorithm differentiable. It is differentiable out of the box, which is very cool. I want to emphasize it even more. There were multiple efforts to run reconstruction with gradient descent with various rendering algorithms, and so far this rendering algorithm has been most successful in this effort. due to its simplicity and flexibility. So I encourage you to appreciate it. Okay, so now that we have defined camera, the algorithm to compute all pixel colors on the image, we can form an image and train our fields using a pretty simple procedure. So recall that in our task we're provided with camera positions and pictures taken from these camera positions. We know the parameters of the camera, the position of the camera, and we can render an image of a scene according to our density field and our radiance field from the exact position we're provided in training set. And we can compute the difference between the image that we've rendered and the image we're given in training set. And with those two images, we can compute mean squared error and just optimize the mean squared error, trying to find such density fields and radiant fields that produce an output image which coincides with the training image. Again, the rendering algorithm is fully differentiable. I'm sorry for missing a parenthesis there. And we can differentiate C with respect to parameters of radiance fields and density field and run gradient descent. On the next slide, I'm illustrating how this optimization procedure works. So usually we tend to start with a density field which is almost transparent. This facilitates training as it allows to pass gradients to all positions on array, as opposed to fields that are non-transparent that does not allow to modify positions behind the non-transparent part. And after initialization with almost transparent part, you gradually find the shape of an object you're trying to represent and gradually improve the overall structure and add details. Let's look at how it works. So the objects form out of nowhere. This video has several phases of training. The first phase reconstruct coarse geometry, and then it proceeds to reconstructing fine geometry with very nuanced details. And it's quite an important feature of the training procedure that you gradually move from a coarse shape, a coarse idea of how the shape looks like, to a detailed shape. The above videos represent synthetic data, and another video will represent real-world data taken from forward-facing camera positions. So camera does not change orientation severely, and this algorithm manages to produce convincing images of real-world scenes. As I've already mentioned, the approach is quite robust and it can be used with different training signals other than attempt to reconstruct an image you're already given. In the second part of this tutorial, we'll discuss an effort to generate 3D models with this approach. In this case, you're using a generative model as a training signal instead of predetermined images. And another pretty cool application, wait a second, let's look at the video. So these models are quite convincing. They have a nice geometry. We'll discuss how to build it later. And another nice application is training not radiance fields, not fields representing colors, but instead we could train fields that represent clip embeddings of images that we have in training set. So we can transform images into clip embeddings of the images, train our field to return embeddings instead of color, and then if we want to retrieve something on a scene, we can compute text embedding of the object we're trying to retrieve, draw a picture, but with clip embeddings instead of color channels, and then compute a scalar product and obtain a heat map of the things we are looking for on the scene. This is an exciting application which can be later used in robotics, in navigation with semantic text queries. Okay, let's summarize NERV and move on to some applications in the time we have left. So I wanted to highlight pros and cons of the original work, which was proposed 3 years ago. So huge pros that allowed for the development of the past 3 years is the simplicity of this approach. It's pretty simple to code. It's the flexibility. I hope that I've convinced you that this is quite flexible with the applications from the previous slide. Another nice feature is that the images we obtain are photorealistic. They are convincing and they are on par or even better than most advanced physically based rendering techniques that are available right now. The algorithm is also secretly a nice compression algorithm. Those training examples started with hundreds of megabytes of training data, of training pictures, and they tend to compress all this data, into a tiny multi-layer perceptron, which takes like 5 megabytes of data on your computer. And this is also a nice prospective application of neural fields. They can give you a flexible lossy compression algorithm. But aside from these advantages, there are several disadvantages that people have tried to fix in the past years. So first of all, the problem we were trying to solve, novel view synthesis, is essentially ill-posed. Here's an illustration of a cat which is standing in front of a mirror. From the point of novel view synthesis, such an image, such a scene, can have 2 plausible solutions if we don't have enough data. One solution is to represent a cat and represent a nice, shiny mirror. And another solution, which can be as plausible, is to model 2 cats standing in front of each other. From the viewpoint of novel view synthesis, those solutions may not differ for multiple viewpoints, but from the viewpoint of 3D reconstructions, the second solution is rubbish. This is a serious issue. Actually, I do not really understand why we're so lucky that neural fields tend to work the way we intend them to work, not vice versa. And other features of other negative features is that the original work, it was very impressive work with nice visual results, but it did not really extend to real scenes you would want to capture in your day-to-day life. I will talk about the caveats of this later. And other 2 issues is that training time is horrible. So as I should have mentioned, to reconstruct a scene, you usually train a single network per scene. You use a single network to model a scene. And training such a network in the original work took about several days with multiple TPUs, huge compute power. And this is not the kind of technology which would be useful to day-to-day users, only maybe to profis. And another issue is that rendering in these models was also quite slow. It took like 1 minute to produce a single image, whereas in computer graphics we typically strive for real-time rendering at high quality. So we now have the problem we also have to solve is to speed up this rendering by several hundred times. Okay. How could we do that? In the next sections of the talk, I talk about efforts in improving rendering speed and efforts in improving quality that led to us being able to reconstruct real scene with modern software. So, first of all, we'll discuss improving rendering speed. There were several solutions behind improving rendering speed. So the problem with rendering speed was quite obvious after the publications, and there are multiple papers addressing those issues. I only highlighted several solutions that allow to speed up both training and rendering inference. And those solutions are the solutions that are most robust and most popular these days. So I'm sorry for omitting nice works that also speed up training. So the first idea, which is so simple that it usually does not get explicitly mentioned in state-of-the-art nice papers, is that the amount of compute we waste on rendering is large. So we have this formula where we compute aggregated color for each ray. We have to compute this color for millions of rays. And the sum here usually involves several hundreds of components. And for each component, we have to compute density at one point of array for several hundred points on array for millions of rays. And color. Each density query and each color query is essentially a neural network query, and it takes some compute power. Computing neural network hundreds of millions of times takes a lot of time. But we know that often the coefficients in this formula are either 0 due to alpha being 0, or they are 0 because we've already encountered some non-transparent surface on the scene, and we cannot see the stuff behind this non-transparent part. And the idea is that we can cache the values of density, and prior to computing density and computing color to obtain the output average color, we can look at our cache and check whether there is something in this point of space or not. If this point of space is empty, we do not compute density, do not compute color, and omit these points of array. If the product terms in the formula above are close to 0, we also omit the summons. And this solution does not take much space. You'll just have to store a cache volumetric grid. And from my experience, this solution already gives you speed up in training and rendering, which is between 10 times or 30 times. So from rendering scenes 1 frame per minute, this solution allows us to switch to rendering scenes at, for example, several seconds per frame, which is much better. Okay, this solution is important. It requires some extra coding efforts, which is already implemented in modern libraries I'll refer to later. And also, there is an understanding that neural networks may be not the best representation for volumetric data. In fact, there is no magic in using neural networks to represent vector fields. You do not usually use neural networks for representing images. So we could have represented volume data Also with not with a neural network, but with a plain simple volumetric grid. So there's an idea that we can switch from neural networks back to classic volumetric grid representations. So in order to represent density field, we'll have to store 3D grid. The usual values are like hundreds by hundreds by hundreds. It takes several dozens of megabytes to store this representation. But we have these days enough GPU memory to store this on the GPU and be able to retrieve density efficiently. And in order to retrieve density with this representation, we don't have to compute any neural networks, any matmuls. We'll just have to go to the exact location in memory and retrieve the value and output the value. Another issue, it's much harder to represent radiance function with volumetric grid because radiance function is essentially not a three-dimensional grid, but it is a five-dimensional grid. So we store volume arguments with a three-dimensional array. And also we have to store colors for each direction on a sphere, for each point in space, which leads up to five-dimensional grid. And if we want a five-dimensional grid with the same granularity as our volumetric grid, we would have to use not dozens of megabytes, but dozens of gigabytes, which is not feasible for modern technology, but there's a nice workaround. So there's a basis set of functions for functions defined on sphere, which is called spherical harmonics. So instead of storing a naive volume grid with fine granularity, we'll again resort to three-dimensional grid. We'll store a vector of coefficient in each in each spatial location, and the vector of coefficients will represent basis coefficients for spherical harmonics to represent a function on a sphere. We'll store three functions on a sphere for each color, and it turns out that to get decent quality, it is sufficient to store dozens of parameters, like 24 for each color. So we end up with a representation that is a volumetric grid that stores 100 floating points at each volumetric point, and it's feasible to store this volumetric grid on GPU and train it. Nice feature of this representation is that querying radiance and density is extremely fast, and it gives you another boost in like 10 or 100-fold. However, in order to get high quality images, you have to store very big, very fine meshes, very fine grids, and there's a limitation to quality, a higher cap that is dictated by trade-off between our memory consumption and rendering quality. There's a different hybrid approach that foreshadows the modern standard solution, and the hybrid approach goes like this. So we'll still use volumetric grid to represent density, but instead of using complex spherical harmonics, which are not familiar for computer scientists, but maybe familiar to physicists, we'll use a thing that is much more familiar to us. We'll use an auxiliary neural network. We'll use a volumetric representation for radiance function. We'll store an embedding vector at each spatial point. I'll call these vector embeddings g of x. They are very fast to retrieve. These are vectors like 12-dimensional, And after retrieving the representation of radiance function at this point, we plug this representation into a tiny MLP, which processes the representation and returns a function on a sphere. So this MLP takes representation embedding and a direction vector D and outputs a color. So if you take a tiny MLP, like 2 layers 64 by 64, it could be much faster than the original MLP, and you can translate the complexity of parameters from the parameters in fully connected layers of MLP that are hard to process, that take time to process. You can translate complexity to volumetric grids. So by far, this approach, this hybrid approach that parameterizes radiance with neural network is most successful. And it produces better quality from the viewpoint of novel view synthesis than the spherical harmonics I mentioned before. So I see that I have 1 minute left, but since we started 5 minutes later, I suggest that I'll finish this part on rendering speed. We'll we'll go on a coffee break, and after the coffee break, I'll finish the lecture and move on to the second part of the tutorial. Okay, so now we have 2 ways to represent radiance fields for novel view synthesis. These 2 ways are using MLPs, which essentially lead to pretty good rendering quality, but they are very slow to render with, to train with. And the deal is that you usually trade off speed in rendering and training for fidelity with MLPs. And another solution that I described is using naive volumetric grids or hybrid volumetric grids that take gigabytes of memory of your computer, but they are extremely fast in processing and rendering. And the trade-off here is the trade-off between memory that we use to store volumetric grids and the rendering fidelity. So in order to obtain high fidelity reconstructions, we have to sacrifice memory. So is there a solution which compromises those 2 features? And it turns out, yes, there is. And the idea I'm going to describe on the next slide is, I think, is a pretty original idea that came from neural radiant fields research, and this is a kind of architecture I haven't encountered anywhere in machine learning. And the idea is the following. So there is redundancy in storing volumetric data with volumetric grids. So most of the points in space, they are empty. There is nothing to store. They store value 0 of sigma. And the color they store, it is not representative. We only care about a small subset of points on the surface. We care about their density, but we don't care about the density of the rest of the points. And the idea is very surprising and smart. So instead of storing a fat, big volumetric grid, the authors propose to define a hash map. A hash map that maps you from an index in a volumetric grid to allocation in an array. And they propose to store an array of embeddings that represents not a single point in a volumetric grid, but all the points that have this exact hash. So how does density query in this representation work? I'll rephrase this. So if we obtain a point in space, we compute the indices of the closest points on the grid. Let's look at the blue grid. So we compute the indices 0, 4, 1, and 7. With the previous solution, we would have gone to memory positions that correspond to these indices, taken the values stored in these positions, and return those values as densities. But this time, we'll do something more complicated. We'll take indices, and instead of going to the exact corresponding position in space, we'll compute hash function of the index. And hash function will map us not to a big array of volumetric grid, but it will map us to a smaller array of a fixed size. And at each point of array, we will store not a density value, but an embedding vector of some dimensionality, like 12 or 20. And the idea is that if there are any collisions occurring, we will try to distill information about those collisions in hash functions into the embedding. And then to obtain density, we aggregate the embeddings for those positions that we've encountered. So 0, hash value 0, hash value 1, hash value 4, and hash value 7. We combine those embeddings, interpolate, and then plug those embeddings into a tiny MLP, which is used only to resolve the collisions that occur in this procedure. And with this hash map, we can effectively store a volumetric grid of extreme granularity with extreme details with a hash map that is parameterized by a relatively small array that resolves collisions using a trained tiny neural network. I didn't explain why there are blue colors and red colors. Those are tricks that are quite common in computer graphics. They parameterize volume grid at different scales, but this is just an engineering detail. This is not as important as this conceptual idea of hash grids for parameterizing volumetric data. I've already mentioned that you can represent other types of data with as vector fields, and the authors of the architecture from the previous slide, they used this architecture to model also high resolution images, and they showed that this solution with no prior data about how compression algorithms work and so on, they tend to compress large images with quite good quality. And well, the picture on the right is a reference picture of an image. And the second picture on the right is an image rendered with a neural network. And neural network is the weights of a neural network take up only 3% of the size of an image in uncompressed form, which is also quite impressive for representing detailed, intricate data. That's all for rendering speed. So to summarize, these days, the way to go solution is a combination of volumetric hash grids and tiny MLPs. And at the beginning of the next lecture, we'll discuss how could you reconstruct rendering quality and shift to real-world scenes. Thank you. So, yeah, I guess you can ask me questions offline and maybe after the second lecture, because I suppose it will be shorter than the first one.